All right. Good morning, everyone. How's everybody doing?
Good. How are you?
I'm pretty good. Pretty good. So chillier in the basement this morning. Apparently, it's cold outside today. Or colder. Mrs. Horn said when I came out, she's like, "Let's play a little game called Guess How Warm It Is Outside." I could tell it's a little cooler in the house, but anyways, attendance. Where's my sheet? Oh well. So Marco, Dawson. Who else? Where's my sheet? Huh. Oh well. So, any questions before we get going? Quick ones, anyways, and bigger ones for the help session as we talked about. All right. So, what do we look at yesterday? We look at the Hooke's law and energy, right? So, Hooke's law to do with how much force a spring applies if you compress it a certain distance, and then the energy stored in the in springs. And so the next step is to sort of analyze further the kind of motion that you get if you have a system like that. And so this little applet or GIF or GIF or whatever you want to call it here, I guess it's GIF, shows what we're talking about, where if we have motion that's sort of repeated pattern of movement here, but specifically where it's always affected by the force from a spring, then you're talking about a special kind of motion called simple harmonic motion. And so we are going to analyze that. So in class, I would have had sort of two different springs, two different like stiffness of springs, and then two different masses to hang on the spring and so on. We can accomplish the same thing with this little gizmo applet. It's free for 5 minutes, and then you have to log in afterwards, but we'll have time to play around with it. So basically the idea that I would want you to look at is like, if you're changing the K value, how does that change the frequency of the simple harmonic motion? And if you change the mass, how does that change the frequency? And so if you're playing around with a stiffer spring, so let's have a certain mass, right? But let's increase the K value. And so to see the frequency it's at there, boom, 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 whatever, it's like fairly fast. And then if you go to a lower, less stiff spring, it's a lower value. And then I could play around with, have the K value be maybe in the middle. And if I went with mass, if I have a tiny mass, it's like bouncing up and down really, really fast. And then if I put a large mass, it bounces up and down slow. Okay, so just very easy to play around with springs to see this and feel this. The heavier mass you put on, the slower the simple harmonic motion, the slower the natural frequency is actually what we're talking about from grade 11, right? But if I go to a higher K value, then I can get higher frequency, right? Really loose spring with a really heavy mass is going to bounce up and down really slow. So that's what we're looking at there. Let me close that page so in case I want to come back to it. But yeah, so we find that a higher spring constant led to a higher frequency, and a larger mass led to a lower frequency. What do I have here for this? Oh yeah, so the K value is proportional to the frequency, or frequency is proportional to the K value, whichever way you want to look at that. And it's inversely proportional to the mass. I have it written sort of backwards here. I'd say more that the frequency is proportional to the, like reverse. I've worded it backwards and shown it backwards as well. But since the frequency depends on these things, people usually write frequency is proportional to the K value, and frequency is proportional to 1/m. Doesn't really matter though. It's true both ways. So yeah. So That's something that you can easily see. And if we're trying to work on an equation for frequency, that's what our goal is going to be, right? You can tell it's going to be like proportional to k and inverse proportional to m and so on, and we're going to work that out. So the next step is to think about simple harmonic motion, and actually this is what we're working towards really here as well, like the idea of like the graph of it. You can see that it's a sine graph, has this like very periodic motion, but it's a very, very special, it's very particular kind of motion that you don't always have if you're letting something repeat, motion patterns repeat themselves. There's a question in your homework, for example. It talks about if you're on a trampoline. If you're standing on a trampoline and you're jumping, like going up in the air, bouncing and going up in the air repeatedly, that's not actually simple harmonic motion, because you're not in contact with the springy surface the whole time, right? So there's a portion where you're flying through the air where you're actually going like free fall or parabolic, like free fall or projectile motion if you're moving sideways at all or whatever. So there's a portion there where it's, even though it's a repeated pattern of movement, of course, it's not actually true simple harmonic motion. So in the homework solution, you'll see that I wrote in there, like it's not as simple anymore, basically, because you've got this free fall uniform acceleration portion of the motion when you're flying through the air. And then the part where you're in contact with the springy surface, that's your section where the Hooke's law applies to it. Anyway, so the link we're going to take advantage of is that we know lots about uniform circular motion, and the kind of motion that you see here of the blue dot is actually the same. It's simple harmonic motion. So if you graphed the blue dot's motion, it would be a sine curve, sine or cosine curve as well. Okay. So you might have seen something like this in actual in your math classes, where the idea of this, as you go around a circle, this is your circle where it's going too fast to analyze here, but this is like your 30, 60, 90, and sine of 30, and then sine of 60, and then sine of 90. This produces your sine curve, right? So the red curve here actually produces a sine curve anyways, and that. So at 30, 60, 90, right? You'd have your 30, 60, 90 would be these values for the heights of that red ball. And so you get a sine curve. And then this one is the same thing. It does actually the same thing, of course, right? It's just the distances are horizontal the way we're analyzing there, just to show it. Could have shown it vertically even, but anyways, so there's a big link between uniform circular motion and simple harmonic motion. So we're going to use that link. Okay. So these applets are broken, so I just left the page here in case they ever start working again. But instead I found these GIFs that are okay. They're not as good as the other ones, but they're not bad. Best I could find. So simple harmonic motion in the math, we're going to use the link between circular motion and simple harmonic motion, circular motion and simple harmonic motion, to give us some equations, right, that we can take advantage of. So for example, in circular motion, we're going to develop the formula for this link between frequency and simple harmonic motion and k values and so on, right? So to start it with, we know that the acceleration for circular motion is v squared over r, right? We know v is obviously so v is distance over time, and then with circular motion, your distance is 2 pi r. So basically, we can get that on the page fairly easily, where we're like, okay, we're taking advantage of our v squared over r, and we know what our speed is for a circle, circular motion, and so that's fairly easy to get down. I'll leave that for a minute here for you, so you can, if you're jotting things down. So we've developed through, and our goal in the end is to have an equation, for the period or the frequency of simple harmonic motion. And you're going to have, that doesn't have the k value in it yet. We're still working on it, and eventually we get to the point where we have, a value for simple harmonic motion. Okay, so that is the goal. That's supposed to be covered up there, but I'm just showing you the idea of what we're working towards. All right, so we have this 2 pi r over delta t squared over r, which we think of as v squared over r. It's the acceleration. So that's going to give us that. If you analyze that algebraically, I could show here a little more detail if you wanted, where basically each one of those gets squared, right? So let's go with blue like normal here. So we'd have the 2 squared is the 4, the pi squared, and the r squared, and the time squared. That's just from applying the square onto everything. That is that simple, right? Because we don't have like it's not 2 pi plus r squared. That would be totally different, right? So that would be totally different. We'd have to do a binomial squared, but this is just each one gets squared. And we're over r, and so the r cancels with that because r squared divided by r is that, and so it's giving us what we had on the other page there. It's giving us the 4 and the pi squared, and the delta t is in the delta t squared is in the bottom, and we have an r up there that was left over as well after we were done. So 4 pi squared r over delta t squared. Okay. So we're interested in finding the frequency, right? The frequency of periodic motion, and of course period of simple harmonic motion, and so on. So the time for a full circle is the period, right? And then we know period is 1 over f, so we can just switch it. We can just swap that out later on. So basically, we know that we can put in, there's a little bit going on here all at once, but the delta t is really just the period, right? And so change that to be period squared. I'm just starting to solve things out a little bit here. So I've multiplied period squared on both sides, divided by the acceleration on both sides. That way we actually have the period squared equation. Okay, so period squared is going to equal 4 pi squared r over acceleration. Since we want the period, we are going to root both sides. Okay, so that gives us a period equation. Technically, of course, we would have plus or minus in here, rooting both sides. Plus, there's 2 options. There's a plus and a minus option. But of course, we're talking about time, right? So we're going to think about the positive one because time is observed to be flowing forward. Quantum mechanics ignored the negative time solution as like normal. Everybody just saw the negative solution doesn't mean anything in this case, and eventually in quantum mechanics they realized that the negative actually maybe has some uses, and that's what led to, if you remember the talk to do with the standard model, we talked about. I mentioned that antimatter particles are really the same as the regular particles, but they're moving backwards in time. So that's one of the ways that you can think about these things. Anyways. The 4 can get rooted, becomes a 2. The pi squared can be rooted, becomes a 2, just a pi. So you can write it like that: 2 pi root of r over a. So, you have to just be able to follow along with this and say, okay, I agree with all these things. I know that v squared over r is true. I know that the velocity is 2 pi r over time. I know if I squared, I get this stuff. I know that, you just have to be able to analyze each of the steps and see if you agree with them, which of course you do. They're all stuff that we've done. We know the period is the time and so on, and algebraically we're getting this so far. Okay, so we've got this 2 pi root of r over a. So this is where the magic happens, where we start to talk about simple harmonic motion. Okay, so the big red arrow saying there's a couple steps involved, right? So for simple harmonic motion, you've got this spring and you're bouncing up and down and so on, right? And so we know, force equals mass times acceleration. And for a spring, F equals kx, right? So if you're looking at forces here, you've got kx equals ma. So we're just applying Hooke's law, Newton's first law, right? So if we are solving for what did I solve? What was I trying to solve for there? I was dividing by a on both, getting rid of the a, getting rid of the k. Solving for x, I guess. See how it works out in the end here, right? Just losing track of what step I was trying to solve for there. Trying to get the R value, I guess, right? Or trying to figure out what R over A is. That's what I was trying to do, because I have an R over A here, right? And so I have a note in there saying like R is really the particular value of X. Like if you're looking at the R for circular motion going around and around, right? The R value is equivalent to here, the thing bouncing up and down, an R value. Okay. So the circular motion version versus the simple harmonic motion version, the R is really just the X value. So this led to R over A being equal to M over K, mass over the spring constant. And that leads to the period formula. A period formula, anyways, a version of it. Oh, this is to get the frequency. Yeah, so that's the period version of it. So we're going to go on our equation sheet. And we're going to add in a formula for, which one here? Circular motion, gravitational potential. I think I already have it added on here. Yeah, simple harmonic motion. So that's where this 2 pi root of m over k comes from. So if you're looking at a question and it says, oh, there's simple harmonic motion and there's a mass and there's a k value, boom, you can just calculate the period because of our application of our circular motion knowledge to get simple harmonic motion equations. Math steps to get the frequency version, pretty obvious, where you're like, okay, that's really 1 over f, right? So we're going to be like, okay, well, too much stuff being shown at once here. I should rejig this a little bit, but all this green part is 1 over f, obviously, right? So I have 1 over f equals 2 pi, you know, just that's the regular equation, just swapped. So if you're trying to solve for the actual frequency equation, you have to like multiply both sides by f. So that's this part right here, multiplying both sides by f. And then you would be dividing both sides by 2 pi, right, to get rid of that. And then you'd be, you know, dividing both sides by root of m over k, but that's when you invert and multiply. Like, just, I think the algebra should be, this isn't a math course, right? So, you know, sometimes I'll show that in more step-by-step detail, but they're just all there all at once, which makes it a little harder to follow. Long story short, or short story long, maybe, whatever, f equals this 1 over 2 pi root of k over m. You don't really need to write both of those down. Like, if you know this one, then you can just figure a period and then say, oh, period equals 1 over f, and just calculate the value, right? So it doesn't really matter. But if they gave you frequency, you might as well just use this formula, I guess, right? And just plug it in, depending what you're looking for. So those are equations to do with frequency and period of simple harmonic motion, right? So those give you frequency and period. Really, it relates back to what we've talked about before, about that natural frequency, right? So we looked at resonance and natural frequency and things like that. And I had masses bouncing up and down on springs. Now you can actually calculate what frequency they would actually bounce at. So it's kind of coming full circle there, giving us extra information we didn't have before. Okay, so just make sure you recognize those have been added there now. Just like yesterday, we added f equals kx in the energy equation. Now we've got equations for what kind of motion they cause. The only other thing to mention in this one is, of course,
go back and pause for a second.
Of course. Let me make that page so you can see the whole thing. Is that big enough for you to be able to see the whole thing? Yeah.
I meant the equation sheet.
Oh, the equation sheet. Okay. Yeah. Well, they're both there anyways, but yeah, I can go to that one too. Plus, this is uploaded as a, you know, to replace that PDF file all the time too. So.
Okay, I have a picture of it, so it's all good.
Okay. Okay. So the last thing to show to do with this was to talk about, you know, in theory, we could say, oh yeah, that'll just bounce up and down and it has this nice, perfect simple harmonic motion. But of course, we know there's friction, right? So if there wasn't friction, it would just keep doing this. But in reality, we know there is friction. Even if it's just internal friction of a spring bouncing back and forth, the spring warms up basically. So friction, of course, causes energy to to dissipate away, and we saw this in grade 11. We called it damped harmonic motion or damped simple harmonic motion. So you get the original curve heights, and then it just dissipates away, right? And so friction causes it away. So that's not really anything new. So basically what we're seeing here is the energy is dissipating away. We're going to talk about simple harmonic motion. Energy would be tomorrow normally, but through the magic of quadmester systems, it's right now. So anyways, any questions about simple harmonic motion? I could have done an example here too on the next page, and it's obviously just, as an example, it says if a 5 kilogram mass has simple harmonic motion due to a spring with a force constant of, I don't know, let's say 80 newtons per meter. Newtons per meter. Determine the frequency. Of the simple harmonic motion. B, determine the period. Either way you did this, the period of the simple harmonic motion, and then we could even do something like I should say here with an amplitude of, if I want to add extra information, with an amplitude of 10 centimeters or something. I don't know if I can do that actually. I better not. Oh no, I can, because you can have any amplitude, because once you hang any mass, it comes down to like a rest position, right, where it's stretched to, and then the amplitude of that is just how much energy you've put into the system. So I was doubting for a second that I could just choose any amplitude I want, because of course there'd be a certain amount of like stretch that this 5 kilogram mass would cause on an 80 newton per meter spring. But that's not what we're talking about. We're not talking about stretch. We're talking about just how much we're letting it bounce back and forth from its rest position. So picture a spring. Certainly you hang a mass on a spring. It has stretched a certain amount based on this and this, right? But now it's at rest, at this rest position, and we pull it down and we let it go, and it goes up and down through simple harmonic motion, right? So if I gave you amplitude with an amplitude of, let's use some commas here, of 10 centimeters due to a spring with a force constant of. And so the kind of question you're going to see in the homework now and then, so I'm adding this in, is determine the distance the mass travels through in 8 seconds or something. I don't know, just choosing numbers at random more than anything here. Okay. So of course you would look at this and you'd say, oh well, geez, what are we given here? We're given, right? We're given m equals 5 kilograms. We're given amplitude equals 10 centimeters. So you're automatically maybe in the habit of saying, oh, that's actually point, divide by 100, so 0.1 meters, and then we're given a k value of 80 newtons per meter, and we're asked for frequency. So you're going to look at that information. You're going to say, oh, wait, I remember we just saw one of these things recently. We saw this. So you're going to pull that equation off the equation sheet. I feel like I should leave the red box there. Actually, just sort of shows. I think I'll leave it. And you plug numbers in. So you just plug in, you get your 1 over 2 pi, root of the 80 over the 5, and you just calculate out a number for the frequency. Okay, so you can see that's just one of those straightforward plug in the numbers. B, if I asked the period, why wouldn't someone just do this? I wouldn't pull out the period equation at that point, right? Or maybe you've only managed, if you're ever faced with having to memorize equations and you've memorized the period equation, well, then just calculate the period and then get the frequency by doing 1 over period, right? Reduce the number of equations you have to memorize if memorization is required. Oh, I better not. I was going to try and, the perfectionist in me was going to try and fix that, but now I'm regretting it instantly here because it's all messed up. Give me a moment. There we go. Good enough. That says 1 over f, doesn't it? So we'd have 1 over that number, and that, of course, give us the period. Okay. Whatever. I shouldn't actually write period there. I should just say number or whatever, certain number of seconds, right? So that's for a full trip, right? That's for a full simple harmonic motion pattern, let's say. So that's like this, right? That goes along with our like full cycle, right? So the full cycle. And so we're talking about that's the period for the full cycle and so on. So when we're talking about the distance traveled and so on, you know, it's going to be 4 amplitudes, right? 4 amplitudes per cycle. So, you know, you'd have your 40 centimeters or your 0.4 meters per cycle. So if we figured out, anybody have numbers for that for me or no? I'm just wondering, like, to get that C value for that 8 seconds, basically you do the 8 seconds divided by the period to figure out the number of cycles, right? And then the number of cycles times 0.4 is going to give you the distance. It's appearing on me. Any questions about that? All right. Somebody need that page a little more, or are we good?
I think I'm fine.
Radio silence other than the one, thank you, that lets me know. I appreciate it. All right, so we are looking at also the energy of systems. This is the energy part I'm going to focus on mainly here. If we were in class, possibly I would have done like a, you know, how you could measure the K value, because it's a possible lab opportunity, because there's 2 different ways you can measure the K value. You can actually just stretch it a bunch of different distances with a bunch of different forces, right, and measure the forces and the distances F and K, and have a table of values and get the slope, and, you know, get the K value by the slope. The new way now that we can do is this one, right? If we can measure the simple harmonic motion frequency, and knowing the mass and the frequency, we can actually figure out the K value. So it's kind of neat that you can just measure the K value 2 different ways and make it happen. But obviously it's not something we're carrying out here, but, you know, the slope of that would give you the K value, and then of course the mass and the frequency would be known values that you measure, and you just determine the K value. So it's just, oops, neat that we could do that if we wanted to. Main event though here is figuring out energy in simple harmonic motion. So of course it's probably obvious, but let's just make sure to emphasize here that you can, when this question here would have been bobbing back and forth here, the energy is alternating between you know, kinetic energy where it's moving, and then up at the end it's going to be stored in the spring, right? And so you'd have energy transferring back and forth between kinetic and elastic potential energy. Often, by the way, they'll say horizontal circular motion. So I feel like maybe I should probably do that right now as horizontal simple harmonic motion, blah, blah, blah. And all I have to do to make just so we don't have to think about gravitational potential energy, right? So I would just group that and move it like that. And then I'll just move everything else. Let's get And just, yeah, if you're dealing with gravity, there's possible complications there as well, of course, right? So this is like fixed to a wall here, you know, and the spring just makes something bounce back and forth, possibly on a surface, or it could just be a rigid spring stuck against a wall. It springs back and forth, right? So my period would be, of course, here, like it was, and so on. So this question as it was would have been fine if we were like in outer space. You wouldn't have to worry about gravity at all. So makes it a little bit simpler to analyze if you don't have to think about gravity. Anyway, so yeah, it transfers back and forth between EE and EK, of course, right? And so if we think about, I'll just show that quick actually with the applet as well, right here. Very similar, well, it's a different applet, but it's in that same gizmos system. So this one we can look at, oh yeah, well, it's not, this isn't for a spring, but you know, the same goes here, right? When the pendulum's up here, it's stored in gravitational potential energy, and then when it's swinging through, you've got kinetic instead, and it goes back to stored, and then it's gravitational and then kinetic. And so the kind of thing you see here with the energies when I press play, you know, you've got the potential energies. Picture this just being a spring bobbing up and down. They don't have an applet for this one, but if it was a spring bob, you know, moving side to side, you'd go between potential energy stored in the spring instead of gravity, and then it would alternate between the kinetic and so on. So you know, this alternates between 1 and 0, as this one alternates between opposite to that, 0 and 1, always just adding up to a total of 1. So this is what I want you to visualize, but just picture it being a spring that's bobbing up and down instead. Okay, so that's the idea. Yeah, so you've got energy alternating between kinetic and kinetic right here, and the elastic potential. This is, of course, the EE, elastic potential energy stored in the spring, and this is the kinetic, of course, energy due to motion, right? So if there's no friction, then those amounts stay the same and just bounces back and forth like this one was here, right? Staying the same value if there's no friction. Yeah. So this one, is letting me control the screen here. Hopefully. All right. So there we go. There's a horizontal spring mounted, blah, 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 and the energy's transferring, right? So I want you to think about when it's compressed way in here, then the kinetic energy's gone to 0, but the elastic potential energy is at a maximum. It's compressed in the spring and stored energy. Then when it goes out to the rest position, this is just where the thing would just sit for days on end, right? If it wasn't moving, at that spot, when it is bouncing back and forth, it won't have any energy stored in the spring. Instead, it'll all be kinetic. So no energy stored in the spring, all kinetic energy, lots of speed. And then it slows down as it stretches the spring. And again, we've got energy stored in the spring at that point as a stretch instead of a compression. And the velocity would go to 0. So picture the energies bouncing back and forth like that other one. So max energy is when you're at full amplitude, basically, either way, compression or stretch is your maximum stored energy, right? So what we're talking about is if we have, you know, the 10 joules of energy all the time, we have our energies are made up of an elastic potential and a kinetic. What do we got here? If there's any friction, of course, it would always be the same, right? So what do I have? So like possible combinations, you know, this is just what I showed on the other page, but we could have 10 joules of energy in the system. So you could have 10 as elastic and none as kinetic. right? So that's at the ends, right? So that's when you have no velocity, and so that's at your maximum amplitudes. I don't know what happened with the little thing there, but yeah, it stores elastic potential energy. That's when you're at maximum amplitudes. So if I copied this picture in there, this one down here, put it on here and shrink it down and circle the two spots, right? So this one, where can I fit this in? Right here. So this, I'll just shrink that a little bit. Holy, that's long. What is going on? My text box is large. It's hard to shrink it down. There we go. Anyway, so I just wanted to give the picture to help communicate what the heck we're talking about, right? So we're talking about these two spots right here. Talking about at full compression and at full stretch. And of course, there's other possibilities. If you have no elastic potential energy stored at all, so you'd have your 10 joules total and you'd have 10 joules of kinetic, right? Where's that? Well, that's of course in the middle, right? So that one, I'm going to shrink that one down too for whatever reason. I want to just shrink that down a little and have room to circle the. So this one we're talking about the middle, where you've got the most speed. All right, so what do I have at the bottom here? Oh yeah, you could have somewhere in between, right? Somewhere in between, you could have an 8 and a 2, for example, and so it'd be somewhere in between. You know, but it looks like probably closer to the maximum amplitude location, right? So you know, in here, oops, that would be somewhere in here, right? So possibly like here and here. So that could be, or that could be somewhere in between, but closer to the max amplitude side of things. Anyways, you get the idea? You got this energy bouncing back and forth, right? So basic work to do with maximum, min, and rest position and so on, right? So the idea of how we figure this out. So if a spring in mass systems undergoing simple harmonic motion, the minimum length of the spring is 8 centimeters and the maximum length is 25. The kind of things you have to be able to do with this. If you're trying to determine the length of the spring at rest position and the amplitude of the simple harmonic motion, this should seem similar and familiar to you as work you've done in grade 11 functions work. If you're trying to get the amplitude of a sine curve or the axis of symmetry of a sine curve, you know, to figure out the vertical shift and so on, it's the same as this, right? So if we're trying to figure out the amplitude, for example, you want to figure out the difference between these two lengths, and half of that is your amplitude, right? Same as finding the amplitude of a sine curve. So there's numbers, you know, this is the concept that leads to the number calculations. What about the rest position of the thing? Well, that's just the middle, right? We want to find the rest position to be the middle of the values, and so you do max plus min divided by 2. This is exactly the same math as you would do in grade 11 for periodic functions, just for that portion of it, right? So let's look at things here. So you know, you have a 55-gram box attached to a horizontal spring with a constant of 24 newtons per meter. It's compressed to a position of 8.6 centimeters, an amplitude of that to the left of the equilibrium position, and then it's going to bounce around back and forth, right? And so it's asking what's the speed of the box at a particular location. And how you're going to figure that out is you're going to think of it like this down here, where it's like, okay, I've got a particular location. I know there's a certain amount of compression, so I'm going to be able to figure out the amount of energy it has as elastic. And then you know the total because they told you the original compression. And so you're gonna be able to figure out how much it has in kinetic, and that'll help you get the speed. That's the idea, okay? So they're starting out with normal processes here where it's like, oh, I'm given all this information, I'm given the amplitude, blah, blah, blah. But I wanna make sure we recognize that one of the key things is to get the total energy, right? So this is the amplitude, and we've got the K value. And so EE, or E total, EE max, I guess you could say, total energy system is going to be your 1/2 kx squared. So we're going to see that in the calculations. But that's a critical thing to notice as a key first step, right? To get those values. Then you can start to analyze, like, okay, what would you have at some place in between? So let's show what we got here. We'll trust that this would have been done here from a textbook version, but we'll analyze it out. So they're saying that the total energy you start with is the same as the total energy that you end up with, right? That's the, I have it in a lesson soon here anyways, but the idea of prime is final, right? So this is initial, and this is final. They use this prime. Prime just means like the apostrophe, but that's just what they call it. So yeah, that little apostrophe there's prime, right? So when you're saying like EE prime and EK prime and so on, that means finals. So initially, okay, so this part right here that I was saying, like, just kind of makes sense to do right away. That's, I want to just do a red star there. That's this. Right, so there's your initial energy. You've got 1/2 Ka squared, so you can get a value. And then the other values work out. So they're showing like you can multiply both sides by 2 and end up with this if you wanted, and then you have a little bit easier numbers to work with. But not critical that you did that, but certainly could. So they are solving for V first. This is the kind where you solve for numbers, solve for variables first. I don't prefer it. Disregarding the negative root, because of course you're just talking about velocity. It doesn't matter which direction, just going to bounce back and forth. But they've solved out for this. So that x squared, right, is like that new position, right? So that's going to be your 0.51 number. So they're solving for the V there algebraically and then figuring it all out, right? But so alternatively, you could have sort of started with just worked with numbers into this, of course, right? To me, it's a little more obvious if you do that, because then you can picture like, oh, there's energy in this form and there's energy in that form and so on, right? So if I were to screen capture that, sometimes some of this is, there's a little bit of working smarter instead of harder, right? Like the idea of getting rid of the 2's and so on, but it's really not that big of a deal, with calculators being fairly easy to push buttons on, of course. But here we would have had the K value of 24. What color do I have there? What K value of the 24? The amplitude is the, what was the amplitude again? 0.086. Right? So this is the total energy, right? And then you'd say, oh, that's equal to how much energy here? Then you'd have your 24, and you'd have your amount that's compressed, the 0.051. Let's shrink this down in a second to make it fit. And then plus this amount of energy, where you're like, oh, I know the mass. So the mass is the 0.55055 kilograms. So say 0.55 there, divided by 2, and you get your V squared, right? So basically you can picture this is the amount of EE, and then of course this is to do with the amount of EK, And so we're able to figure it all out. So I think I can probably just move everything sideways. Give myself room for this analysis where we're showing the individual energy concepts. I get why they show it the way they do there, but I think that it's just nice to sort of see the idea of those energy values, because in the end, you have this V equals this root of whatever, and it means nothing to anybody. So obviously you can just solve for V, right? Okay. So that's the speed when you're at that spot. The other question they ask in part B is what's the maximum speed? Well, of course, we know from what we've analyzed, maximum speed is going to be when we have no elastic potential, right? So it's going to be in the middle when you have no elastic potential at all. So really, we're just equating this value here. So it's kind of nice to have this value as a number, right? That number, whatever it is, right? It's nice to have that because then you can set that equal to EK and solve for V. So what did they do here, though? Their version of it. All right. So when x equals 0, yeah, they're using that V result. But you could do that, or you could show good understanding saying when x equals 0, but or picture all energy is EK, right? And so you have your total energy, you have your I want to say ET, right? But whatever that total energy was as a number, which we got already, equals the 1/2 mv squared. So the number that we got for the energy. So I feel like maybe we should calculate that. I started off saying that that's what I would probably have done, right? So what does that give us as a value? 1/2 of the 24 and our amplitude of 0.086 squared. That gives us 0.086 squared times 24 divided by 2. I'm getting 0.0088752. So that's how much energy is stored in the system. So that 0.08872 number would be right here. And so that would equal the 1/2. The mass is 0.055 and v squared. So that number times 2 divided by 0.055 rooted gives us 1.79. Just solving out 1.796 ... which of course is the same as that one, 1.8 meters per second. So I would say that it's good for me to show you both ways, because clearly I think this way is the most understandable. It's like using the concepts directly and saying, oh, the total energy is going to be all kinetic because we're at that stage where we've, our maximum speed, we want all of our energy is kinetic, of course, right? It's so obvious. And so I strongly prefer you do it this way because it's just so logical. What you're going to be faced with, though, unfortunately, is this other form of things that textbooks often do, where they just have these. And the reason for this, by the way, I should point out, the reason for this is so that you don't have to try and keep all these numbers, right? So basically, this makes it so that all numbers are kept, right? All numbers are kept. Right, which is what I'm saying to do anyways. Keep as many numbers as your calculator will let you all the way through, right? When they do this divided by this, and then times that, they're not going to round this to 1 or 2 significant digits or whatever, and then multiply. They're just going to divide, multiply, and get a number, and then round to 2 significant digits. They're not going to round here, right? So this is not rounded. It's just a calculation, right? And so we accomplish the same thing by being very logical about what we're doing. Energy is kinetic energy, and so boom, boom, we can solve. Just keep all your decimals. Keep as many decimals as your calculator let you on the way through, same as you would do in this step. And so that's why textbooks prefer to and tend to show like this, because it gets around that whole, like they never really say it properly in the books. Like they never really say, oh, keep all digits till the end for some reason. But that's effectively what they're doing. They're just avoiding the concept, the discussion by solving for the variable you're looking for algebraically, and then just plugging it all in. Any questions about that? All right. So main idea of the energies, don't have to algebraically solve for that. I'm not demanding that or hoping you do that at all. I'm hoping you do it the easier way. So this one is solved out as well, but you've got a total mechanical energy in a system. So instead they're giving you the total energy. So right away you should be thinking, oh, okay, if the total energy in the system is that, then that means that at our maximum, that's like E equals 1/2. Yeah, thanks computer, that was great. Equals 1/2 m kx squared. Sorry, 1/2. It's elastic potential energy stored, right? 1/2 kx squared. So basically the amplitude, right? At the full amplitude, you've got your max energy. So it looks like right away we could say, oh, so we get 7 joules equals 1/2 of a spring constant force of 120 and a squared. Obviously, we're going to be able to solve for what the amplitude is, right? So just solve for what the amplitude is, and all of a sudden now you know what the amplitude is. That's the idea of it. So again, it's basically they gave you something, right? This is the 7, and so plug it in and solve it out and so on. Max speed, well, and for this one, like we said in the previous one, all energy, right? All E equals EK, right? So that 7 joules, 1/2, where's the mass of this thing? Total energy, block, the spring, frictionless. Give us the block. Interesting, maybe just give it a mass later on. Let me jump ahead to see what the solutions had to do with that. Because you'd need, yeah, so 0.55 kilograms. Did they tell us that in the system here? That's forgotten there. Anyways, so obviously we needed it. So 0.55 kilograms and so on. Because the speed you get from a spring with a certain amount of force obviously depends on the mass, because F equals ma, right? So anyways, I'll just leave the rest of that one for you to go through, or do you want me to go through it bit by bit? What are we thinking? We do have lots of time, so should I keep going?
Could we try going through it? Sorry.
Yeah, sure. Yeah, let's do that. So they did need to give you the mass there, of course, right? The 0.55 kilograms. So the first two steps we've kind of done here, but obviously you can just calculate them out. And then the last two are a little bit different thoughts, so give it a try. Does everybody have a copy of that page there so I can save files while you're working? Put the numbers you need for it. just let me know if you need me to bounce back to that screen at any time there. I'm just gonna get some of this done so I can post it for you as soon as possible. Export that. Better. Part. So I just calculated the number there, just multiply both sides by 2 and divide it by 120 to get 0.34. And then for the velocity, I multiply both sides by 2, divide by 0.55, root it, and I got 5.05 or 0.45. 0.45. So if we're working with 3 significant digits, looks like I don't know if it's 3 significant digits, 2 to be honest, so we'd either call it 5.05 if there's 3 significant digits, or 5.0, I guess, if it's 2 significant digits. I'll just show the first 2 there, the A and B, just what they had. Of course, they're saying, okay, the maximum energy occurs when it's all, maximum amplitude occurs when you have all of your energy as elastic potential. So exactly as I showed. So, and then they solve for X and get 0.34. This is just the result of course, multiplying both sides by 2. So you could say, or 7.00 equals 1/2 k x squared. Oops, I messed up the k value in. 1/2 of the 120. 0.0, that's 4 significant digits the way they're giving it. X squared, and so we're going to say multiply both sides by 2. Give us 14 equals 120.0 x squared. Divide both sides by 120. Oops, a little sloppy there. X squared equals whatever that is. 14 divided by 120 is 0.116 repeated. Keep a bunch of decimals, of course, and then root that, and you get X equals 0.34156 ... I'll show that in the homework a lot, where it's just ... dots, showing like basically I got a bunch of numbers, but of course I can only trust those, right? So 2 significant digits, because I believe somewhere along the way they gave us 2 significant digits. So basically, even though the K value of the spring is known so precisely, the mass is approximately 55 kilograms, which gives us an answer in the end here of approximately 0.34 meters. Make sense? So it's interesting, actually. I've got 3 significant digits, 4 significant digits, and only 2. So of course we rounded to 2 in the end, right? The least number of, right? The least number of significant digits we had and what we're given. And the other part that I already showed as well was this, where I gave you, obviously, the maximum speed is going to be when all the energy is kinetic. And so same deal here. So the solving by the same process, multiply both sides by 2, divide both sides by the mass, root it, you get 5, which is what I had up here somewhere, yeah, 5.05 or 5.0, depending on how many significant digits you're thinking you should keep. Right? So those are we already talked about. Are we ready to look at part C? Anybody want to wait a little longer for part C, or should we go for it?
I think maybe go for it. I wasn't really sure how to get started.
Oh, okay.
Please go for it.
Yeah. Okay. So I'll show what the page has here, and then possibly I'll end up showing like an even better way or whatever. But we'll see. I think this has worked out pretty nice, actually, if I recall. So the idea of the total energy of the system, right? So this is total energy here. Right, so that's going to be your amplitude compression stuff, right? So they're going to end up showing that probably somewhere, but oh yeah, it's all right, I guess. But what do we want? We want the speed, right? And so because we want speed, they're solving for that kinetic energy, right? Because we want speed, and so you're going to have like a 1/2 mv squared equals the other stuff, right? So that total energy is this one here, right? The total energy was at maximum amplitude, right? Which we did in part A. Is that right? Oh no, they gave us the total. Yeah, they told us the total energy flat out, right? So total energy, I'm just going to say given, right? Total energy was given. So the trick is now to think, okay, well, what is this energy made up of at any spot? And so maybe instead of solving right away, I might just show that where you've got the 7. Stop it. Keeps pretending I'm erasing and stressing me out. All right. So we've got the 7, 0.00, the total energy. And we're saying that that's equal to, at any point in time, the kinetic energy plus the elastic potential energy, right? And so we want to know what the speed is when we're at 10 centimeters. So we want to know what the speed is. So 1/2 of the m, which is the 0.55 v squared. We're looking for the v value. And we know that adds up with the 1/2 kx squared, 120.0, but for calculations, it doesn't really matter. You're just keeping the number of significant digits in the end. So I wouldn't bother typing in 120.0. I would just type in the 120. But this is your x squared, right? And that x value is given as, let me just undo, that's given as 10 centimeters. So 0.1 meters. So I'm hoping that we'll get to the point where we won't be stumped at the start of this. Basically, there's your total energy, right? And it's equal to the 2 added up. So there they are, just the 2 added up. And basically now you just have to solve for V. So the concept was that my total energy in my system is always there. It's just going to bounce back and forth between kinetic energy and elastic potential energy. So they're telling us the spring's compressed by 10 centimeters. Oh, okay, so there's the energy that's stored in the spring. Figure out the value for the velocity that results, right? So they're going to have the 0.1 in there and so on. But the way they're showing it here, just to me, it's just carry out the algebra however you want at that point, right? So get this as a number, get that as a number, subtract that from both sides, divide that from both. Like it's not too bad. So if we did that, we'd have undo here. 7. We'd have the 7. Again, for calculations, it doesn't matter whether I write 7.00. That's for my analysis at the end, right? So what is the 1/2 of the 0.55 divided by 2 gives me 0.275. That's my v squared with it. And then over here, I've got whatever I've got here. So, oops, I forgot my squared there. Kx squared. So 0.1 squared times 120 times 0.5 is that 0.6 number over here. We would, of course, take away 0.6 from both sides, as I mentioned earlier, and give us this number here, 7, take away the 0.6, which of course would just be 6.4, but I was going to type it in, but that'd be silly. Waste of battery, 0.275. Now, would I actually still type that in on a test? Yeah, probably, because, you know, got to make sure, right? So take away the 0.6, I get my 6.4. Now dividing by 0.275, of course, is that. Not of course, but the calculator gives you a value, I should say. 23.272727. So for me, I'm keeping as many as I can. So I'm going to show repeated numbers there. And I have it in my calculator still. I can just hit root. So v equals 4.824 dot, 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 dot. And you're like, okay, what did we have? The lowest number was 2 significant digits as we had before. So we're going to say 4.8. Okay, so they end up with a 4.8 there by a similar process, but they just mess things up by solving for v first. To me, it just makes it harder to follow. The benefit of not having to talk about significant digits on the way is I just don't, it's just not worth it to me at all. What do I want to do for this one? Let's go ungroup there. Let's just want to make it a little bit, this page a little bit easier to follow. Bear with me here. So if I lock that in place, I'll be able to just grab this and group it and move it around a little bit. There we go. A little easier to follow. Is that good now? Like, I think it was Sarah, you keyed your mic and you said you weren't sure where to start. Do you get the idea of it now, where you can put in the
Yeah, that's okay.
spot?
It's
Yeah,
just
okay.
like, it can sometimes be like a bit overwhelming, like remembering how everything relates to everything. Like I just need practice, but
Yeah, exactly.
Yeah.
And that's exactly what comes next is practice it, look at the homework solutions. But the main driving principle was exactly what we kept saying here is the idea of your total energy is just your elastic and your kinetic added up. So they essentially gave you the, they gave you the elastic by telling you where it was and then allows you to figure out the kinetic. And associated with that kinetic is the speed. So totally understandable. Part D, what did it say again? Part D said, oops, not that one, this one. Part D said, what would be the period? Oh, that goes back to the equation from the previous lesson, right? So for the previous lesson, we would look at our formula. That's not what I wanted to click on. We'd look at our period formula, 2 pi root of m over k. And so we know the k value is 120, gave some mass of 0.55, boom, just calculate out the period, right? So just would have to refer to your equation sheet and use the formula, right? Plug in the numbers, get a value. Okay. All right. Anybody need that page a little more, or is I think that one's, or you would just say, oh, I'm just going to use the other equation, right? So that's the file for the questions for that one. This this part here is just, these ones here are just the energy stuff, if I recall, and this one is actually like a review questions. So you're going to have some in here that are just to do with like, you'll see there's going to combine some ideas there. These are a little tougher questions because they combine more than just one concept at a time. They're all solved out though for you to be able to refer to for help. So again, I would highly recommend you work on those right now. These questions and these questions right here, because of course I'm available by voice and sharing and everything right now. So if you run across any problems, you can ask right away and not have frustrations of time delays. Okay, so please work on those. Like if we were in class right now, I'd say, hey, work on these so I can help you. So make online as almost as good as being at school. Work on stuff so you can get some help. I can help you. So I will finish PDFing and uploading so you have the actual files. I'm assuming you probably took screenshots of these questions anyways already, but this will be up on the website shortly. Smart question answers, 46 answers, 46 lesson. Should do it. So those are uploading as I speak. They're almost there now. There they go. They're there. And I'm still here. I'm going to work on solutions for the next stuff while you guys are working. If you have any questions, just key your mic, and I'm right here for you.